Hello everyone. This video is on the Knewton Alta assignment for section 5.1 part 3 called Applications of Quadratic Functions. Alright, so in this video I'm going to be doing a preview version of this assignment. So please understand that the questions I see in this video may not be exactly the same as the questions that you see when you work on the assignment on your own. But all the objectives are the same, so I'm hoping that watching me do a few of each objective here helps you out in some way when you work on the assignment yourself. Alright, so on your assignment page you should have the title, the mastery bar. You can see your objectives. Looks like there are 4 objectives for this particular assignment. And then under the current objective, you should see a question related to that objective. And at the bottom of each question, you should see a feedback button where you can send feedback to Knewton. You will not have the instructor cheat button. It's for instructors only. But you will have a more instruction button. If you're ever struggling with a particular topic, try clicking on more instruction. You'll be taken to a page with further reading or videos, and you can see questions related to that instruction. And there's nothing wrong with getting through the assignment that way, using more instruction for each question if you want. Alright, so the first objective I'm seeing here, determine the maximum and minimum values of quadratic functions. So basically, the maximum or minimum value of a quadratic function is going to be the y value of the vertex. We'll see when we get into this question here. So a farmer is building a fence to enclose a rectangular area against an existing wall, shown in the figure below. Alright, so you have this wall that's already there, and the dotted lines are the fencing, and the fenced in region is a rectangle. So yeah, 3 of the sides will require fencing, right? That's these dotted sides here. And the 4th wall already exists, as they've said. If the farmer has 144 feet of fencing, what is the largest area the farmer can enclose? So let's go to a picture. I'll draw a piece of paper. So again, you have this wall that's already there, and we're putting in fencing to make a rectangle. And then there's some area in the enclosed fencing. Right? Now, they said the farmer has 144 feet of fencing. And then they're asking, what is the largest area possible? What's the maximum area? Question mark. Alright, so what are some possibilities here? Now, you don't have to do this. Alright, if you already know how to do this stuff, go ahead and do it the way you know how to do it, the way you properly should. But, let's play around with this. Here are some possibilities. So if you have 144 feet of fencing, we could just cut it into thirds, right? There's 3 sides of fencing. Or if I divide this by 3, that'd be 3 times 48. Alright, so I could have a 48 by 48 by 48 here. Make it 48 feet here, 48 feet here. 48 feet here. And then, you know, the area, right, this area here would be just, you know, remember a rectangle, it's just length times width, so that'd be 48 squared. Right, and 48 squared, just kind of have a calculator off to my side here, is 2,304, and that would be, you know, square feet. Square feet. So, I mean, that's one possibility. Another possibility is, you know, I again have this fencing, and you know, maybe I shave a few feet off of the widths here and add it to the length, or off the lengths and add it to the width. Like if I take 2 feet from both sides, you know, because whatever you take from one side, it has to be taken from the other to keep it a rectangle. So I mean, I could take let's say I take 8 feet off, make it 40 feet, 40 feet. Right, so that's 80 feet, and then the other 64 feet would have to be on the width. Right. So I could do that. I could make it a 40. You know, that's 80 and 64. That's 144 feet of fencing. What's the area here? Well, the area here, I'll just use A for area. All right, capital A for area from now on. Would be 64 times 40, and that's 240 plus 16, 2,560. And let me just double check that with my calculator off to the side. Yeah, 2,560 square feet, which is more. So this little square I made over here isn't the maximum area. But then you got to ask yourself, you know, is this one I made here the largest area? I don't know. How do we figure this out? How do we figure this out? Okay. Well, just like any other word problem, you read through the problem, which we've done. Hopefully you understand what they want. And then, you know, ask yourself, what are the unknowns here? What are the unknowns? Well, I don't know how long to, I'll call this the width actually. I don't know how wide to make the fencing and how long, right? I don't know the width and the length. And if I don't know the width and the length, I don't know the area as well. There's a bunch of unknowns here. But you got to remember something about a rectangle though, that area equals length times width. And we're going to keep that in mind. Because if we're asked to find the largest area, I'm going to want to have an equation for area. And then we'll find the largest value of it. Alright, so let's say I call the length x. So that's x feet, that's x feet, right, on the other side. So x feet, and use the fact that we know we have 144 feet. So the width would be 144 minus 2x, right? If I call these lengths x and x, they make 2x together. So whatever's left, 144 minus 2x, that would be the width. I hope that makes sense. So then you see when I put these into my area function, my area formula, we get a quadratic function. Right? So the area is, you know, length times width is x times 144 minus 2x square feet. And this is actually a quadratic function in x. All right, I'll call it a of x. You know, the area with the area of the rectangle with this length x. And if you distribute x here and we can put this in general form. You know, put the highest power term first. That'd be negative 2x squared first, and then plus 144x. So you see, It's definitely a quadratic function, ax squared plus bx plus c. And if we're trying to find the largest value of the area, let's look at a graph of this. You know, I have my horizontal axis will be x, my choice of length, right? My choice of length x. And then the vertical axis will be values of A, right? The outputs are areas here. And the maximum value will occur at the vertex, right? This is a parabola opening down, right? The lowercase a, the lead coefficient is -2. So this is going to be a parabola opening down like this, right? Meaning it's going to have a highest point. There will be a largest area, and that is what they're asking us to find. What is the area, the output at that highest point? So remember, ax squared plus bx plus c, the lowercase b is 144. And hopefully you remember from previous sections, you know, previous videos, section 5.1 part 1 and 5.1 part 2, the axis of symmetry was x equals, you know, the opposite of b over 2a. This is basically the x value of the vertex. You know, this is that vertical line that runs through the vertex that cuts the parabola in half, that it's symmetrical about. So -144 divided by 2 times a is -4. And, you know, when you divide these two here, that'd be positive 36. So at x equals 36, if I have a length of 36, that's where the axis of symmetry is going to be for this parabola. And the vertex will be on this. And, you know, also I'm hoping you can see that when x is 0, you have 0, 0. And if x were 72, because of this factor here, you'd also have 0. And can you see that 36 is exactly halfway between these? Right. And then you're going to have a parabola. Right. Now we just need to know what that highest point is. Well, remember how to find, you know, this is the x value of the vertex. How to find the y value, just plug it in. What is a of 36? So you can plug it in here, or in the factored form. It doesn't matter, they're the same function. I'll go back to the factored form. So that'll be 36 times 144 minus 2 times 36. And that's 36 times, you know, 144 minus 72 would be 72. And I'll punch this in my calculator. 36 times 72, 2,592 square feet. 2,592, and that's going to be the vertex of this parabola. All right, and I'll draw a rough sketch of that. Like, you know, it's going to look like this. And look, my pictures earlier, those little possibilities I put up. You know, here is what happens when the length is 48. Remember, these I was calling x. When x equals 48, we get an area of 2,304. All right, so when x is 48, we had this point here. This is 48, comma 2,304. Right. Then this picture I drew here was when the length is 40. Right. When x is 40, we got an area of 2,560. Right. This would be the point 40, 2,560. But you see, those aren't the highest values of the output. Those aren't the highest areas. The highest area is this one here. There's the max. 2,592, you know, square feet. And that would happen when that length is 36. All right, so if I was drawing that picture again, here's the wall. I make these two lengths 36 feet. That'll give me the largest area possible. And if those are 36, right, then the width is 72. Right. So 36, 72, 36, that's 144 feet of fencing. And then this is the area here, the area taken up by this fencing, and that's the largest area possible. Now, the key to all this And you'll see it's the case for a lot of these word problems. They asked me to find the largest area. So the goal is to use what you know about rectangles or whatever shape you're given to write an equation for area that is a quadratic function of some variable. And then if it's a quadratic function, that's opening down, you can find the largest value of it. If they wanted the smallest value of something, you're going to write a quadratic function for that's opening up so that it has a smallest value, a lowest value. But that's the goal. That's the goal for all these. If they ask you to find the largest something or the smallest something, the maximum something, the minimum something, you're going to end up trying to write an equation for that something that's a quadratic function. All right, so it'll involve some substitution. It'll involve, setting up pictures and whatnot. That's probably the trickiest part, is knowing how to set up that function, and it changes from problem to problem. All right, so I'm just hoping that watching me do a few of these gives you some sort of guide as to how to approach some of these. All right, not every single one's going to be the same. But the answer though is 2,592 square feet is the largest possible area that this farmer can enclose. 2,592. All right, then after you submit an answer, it'll tell you if you're right or wrong. Sometimes it'll give you another chance. And then it'll give you an answer explanation. Please read through the answer explanations, whether you're right or wrong, just to make sure you understand what's going on. Especially if you're wrong, right? Try to learn from your mistakes for future questions. Okay. Next question. So this is another one where, now this one they're going to give you a function, use a quadratic function to model projectile motion. So this is just if something's thrown into the air, right? An object is thrown through the air, that's a projectile. And the motion it would take would be like an arc, it goes up and then comes down because of gravity and all that. So they'll give us, here they're giving us a function that models some projectile motion. So here, a model rocket is launched directly upward at a speed of 28 meters per second from a height of 12 meters. The function f of t equals negative 4.9 times t squared plus 28t plus 12 models the relationship between the height of the rocket and the time after launch. So t represents the time after it was launched in seconds, and f of t represents the height off the ground, right? The height of the rocket. How high is it off the ground? That's f of t. So the question is, when in seconds after launch will the rocket hit the ground? Do not round until the final answer, then round your answer to 2 decimal places. Right. Okay, so I'm going to draw this. I'll write out all the information we were given. Let's grab a little paper here. So we have, f of t equals, negative 4.9 t squared plus 28t plus 12. And I'll start graphing this. Now the horizontal axis is going to be values of t, right? This is time in seconds. And then the vertical axis will be f, which is going to be height in meters. And I hope you see that when t is 0, the height is 12, right? They told us that. So there's a point on the graph of this model. They said that the rocket was launched, initially from a height of 12 meters. And then it's going up and coming down, right? Something like that, because it's going to be it's a quadratic, ax squared plus bx plus c, but instead of x we have t. And you see a, the lead coefficient, is negative, so it should be some parabola opening down. And then where does it hit the ground? Well, that's here. Hits ground. That's when f of t is equal to 0, right? When the output is 0. In other words, t-intercept. Or if this was x, it would be the x-intercepts. So, and then you'll see we have another objective in this particular assignment. That's on finding the x-intercepts, or in this case, the t-intercepts. Remember, this is just let the output be 0, right? Just when is the output 0, and then you solve the corresponding equation. So we're going to let f of t be 0. So f of t is 0, and then equals, negative 4.9 times t squared plus 28 times t plus 12, and we solve this equation. Solve for t, and then see which values actually make sense for the rocket launch problem. Now, this is set up in a way that I can use the quadratic formula. All right, we have everything on one side, 0 on the other. It's in general form on the other side, 0 on the other. We can use the quadratic formula to get our solutions here. So remember, it was t equals, or x equals, the opposite of b, the opposite of the linear coefficient, so negative 28, plus or minus, and the square root of b squared, right, 28 squared, minus 4 times a is the linear, the quadratic coefficient, the lead coefficient, negative 4.9, times c is positive 12, right, the constant term, all that's in the square root, and then all of that is divided by 2 times a, 2 times negative 4.9. All right, and I'm going to enter these into our calculator. Now, I'm going to actually show you this time the calculator I'm using. And you can just go to there's a free online graphing calculator at desmos.com. Right, that's easy enough to use. Desmos.com is totally free. And I'll enter these values. So in the numerator, I'll put, because it has multiple terms, I'll put it in parentheses. We have negative 28. I'll do the one with the plus. The square root, just type SQRT. And then inside the square root, we have b squared, right? 28 squared. Minus 4 times negative 4.9 times 12. Just make sure that's all in the square root. Close the parentheses, divided by, and then 2 times negative 4.9. I'll just put negative 9.8 because that's what it is. All right. Okay. Let's make sure. All right, so that one, see, is a negative time, so that's not a good one. Negative, if I round that to 2 decimal places, that's negative 0.40. So negative 0.40, that would be over here. If the parabola were to continue this way, that would be this value here, right? Where you hit the t-axis. But that doesn't make any sense with the rocket launch, so it's got to be the other one. All right, so let's see what the other one looks like. Now I'm just gonna, nice thing about this is I'm just gonna copy and paste it and replace the plus here with a minus. Right. So I'm gonna, oops, copy all this, Control C, Control V, and then just replace this plus here before the square root with a minus, and you see 6.114. Round that to 2 decimal places. That's 6.11 seconds. Right? So the other one is approximately 6.11 seconds, and that's here. That's this other point where it hits the horizontal axis, hits the t-axis. And that's the one they want, right? Obviously, because again, the other one doesn't make any sense with the problem, right? How can something hit the ground back in time, right? In a negative time. All right, so after all that, when is it hitting the ground? Rounded to 2 decimal places at 6.11 seconds after launch. Wonderful. And again, please read through the answer explanations. All right, so now what I just did there was basically find the x-intercepts of a quadratic function. You set the output to be 0, and solve for x. And you might, you can use the quadratic formula, you can do factoring, you can do completing the square. Whatever you remember how to do to solve a quadratic equation, do that, and you'll find your x-intercepts. And of course the y-intercept is easy. Replace x with 0, and then you'll get the y-intercept. That's probably the easier of the two. So here, now I know they want the y-intercept, but I'm going to show you both. How do we find both? All right. So here we're given, f of x equals -1 times x squared minus 2x, and then plus 24. And say I wanted to find the x-intercepts. Well, again, just let y be 0. Let the output be 0. So I replace f of x with 0, and we get 0 equals, -1x squared minus 2x plus 24. Now, this is in a form where I could use the quadratic formula again, but this is also nice and factorable. If I pull out a -1, we'd have x squared plus 2x minus 24, and then this factors to x plus 6 times x minus 4. And we can see from the zero product property that x equals -6 or x equals +4, right? What makes these factors 0. And these would also be the values that came out of the quadratic formula. If you use, a is -1, b is -2, c is 24. If you use the quadratic formula with those values and simplified, you'd get -6 and +4. All right. So the x-intercepts are -6, 0, and +4, 0. And then the y-intercept, again, is very simple. Just let x be 0, right? If you're on the y-axis, the input is 0. And so f of 0 is simply, the opposite of 0 squared minus 2 times 0 plus 24. It's just 24, right? Everything with an x in it would just disappear. And so 0, 24. There's the y, and that's what they want in this particular problem. All right. And then they do ask us to enter as an ordered pair, right? So 0, 24. Just the y-intercept. Great. All right, then same function. Now they want the x-intercepts, and I already showed you. And again, these are real solutions, right? These are real numbers. So when you go graph, those points would be on the graph, right? You would have -6, 0, there'd be a point, 4, 0, there'd be a point. The only reason I'm pointing that out is because sometimes quadratic equations have imaginary solutions, right? Square roots of negatives. And if that's the case, right, if the equation only has solutions with imaginary numbers in them, then there are no x-intercepts, right? Because remember, the x-axis, this is a real number line, so there's no imaginary numbers on it. Right? So if you come across any imaginary solutions, you're not going to have x-intercepts in that case, right? I'll just point that out now. But we do have some here, right? -6, 0, and 4, 0, and they're asking us to enter those as ordered pairs separated by commas, right? So parentheses, -6, 0, there's one x-intercept, comma, and then 4, 0, the other x-intercept. Great. All right, next question. So there's find the domain and range of a quadratic function. Now the domain is all real numbers. This is a polynomial function. There aren't any denominators with variables. There aren't any even roots or special symbols. So the domain is all real numbers, and you notice that that is the option for all of these anyway. So the domain is all real numbers. But the range, to find the range, you need to know the vertex and which way the parabola opens. So once again, let's go to some paper here. I'll write this function out. So we have f of x equals, negative 3 times x squared plus 12x minus 7. Now again, the domain, the values of x that can be used is anything, any real number. So the domain is all real numbers, right? Everything from negative infinity to infinity on the x-axis can be plugged in. And that's the case for any polynomial, not just quadratics. Right? And you'll learn more about polynomials throughout chapter 5 of this text. It's the range, right? To find the range of a parabola, of a quadratic function, you need the vertex, or at least the y value of the vertex, and which way does it open? Which way does the parabola open? Now, this is in that general form, ax squared plus bx plus c. The value of a is negative 3. It's a negative number, meaning the parabola is going to open down, right, like this. Okay. So the range will be from negative infinity up into whatever the y value of the vertex is. All right, now the value of b is positive 12. Then we can use this to find the axis of symmetry, AOS, equals, the opposite of b, negative 12 divided by 2a, which is negative 6, that's positive 2. There's the x value of the vertex. I plug that in to get the y value of the vertex. All right, now f of 2 would be 5. All right, it'd be negative 12 plus 24 would be positive 12, minus 7 would be 5. Okay, plug in 2 for x. So the vertex is 2, 5. Right, and I know the parabola opens down. So it's doing something like this. Now it doesn't look exactly like this. I mean, it's going to cross at 0, negative 7. This is actually a bad drawing. But all I need to know is the vertex and which way it opens. So you see the range is everything from the bottom, from negative infinity all the way up to 5, right? So the range of this function in interval notation is from negative infinity up to 5, including 5, right? Because this point here, the vertex has an output of 5. Or all the values of y, or all values of f of x less than or equal to 5, right? You could say that too. And that's what they have in the options. So domain's all real numbers. F of x has to be less than or equal to 5. That's this last option here. Good. And again, look through the answer explanations. Doing the same thing I showed you. Alright, so back to some word problem. It looks like this one involves rectangles again. Remember, just the area is length times width. So here a farmer is building a fence to enclose a rectangular area consisting of 2 separate regions. So these 2 regions here. The 4 walls and 1 additional vertical segment to separate the regions are made up of fencing, as shown below. If the farmer has 648 feet of fencing, so all these dotted lines here, even the one in the middle, add up to 648. What are the dimensions of the region which enclose the maximal area? Maximal means maximum, largest. So I'm going to try to find the largest area that you can enclose with 648 feet of fencing in a region like this. And then they want the dimensions, so they want the length and the width. What's the length and the width? So many feet by so many feet. Alright, so once again, I'll go to a piece of paper. I'll draw this picture. So making this rectangle, the dotted lines here are fence. It's all fencing. And there's one in the middle somewhere to separate the areas. Now, let's call this x feet, this vertical length, and then this would be, since these are rectangles, this would be x feet as well, this would be x feet as well. And there's a total of 648 feet of fencing. Alright. So what's left would be 648 minus 3x, but then we need to cut that in half. Alright, because these two sides make this up. So we cut this in half now. Half of 648 would be 324 minus, and then 3 halves x. Right, cut that in half as well. Right, so there's 324 minus 3 halves x feet on this side, and the same thing over here. I hope that makes sense, right? Because again, if I call these x, it'd be x, 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 that's 3x. So there'd be 648 minus 3x left over, but then there's still two sides left, so we got to cut that, cut that in half. 324 minus 3 halves x. So then the total area, right, the total area taken up by this big rectangle, which I'll call a of x, right, this is area, is length times width, x times this 324 minus 3 halves x. And if you distribute the x, you'll definitely see, and put it in descending order, put it in general form, you'll see it's a quadratic function. And that's the whole goal of all these, is to get what you're trying to find the largest of or smallest of to be a quadratic function of some variable. So we have negative 3 halves x squared plus 324x. So this is going to be if I graph this, right, so x is these lengths here. I got the x-axis, and then a is the areas. This is going to be a parabola opening down, so there's going to be some maximum area. And I hope you see that when x is 0, you get 0. Alright, when x is 0, you get 0. And then, maybe you see it, but if I were to set this factor to be 0, right, because if I want to find like the x-intercepts, set this a of x to be 0, x is 0 would make that work. And then 324, times 2/3, so 108 times 2, 216. If x were 216, you'd also get an area of 0. And then using symmetry, you can find the axis of symmetry. Half of 216 is 108. Right? That's where the axis of symmetry is going to be. But let's see that actually work out. Little a would be negative 3 halves. Little b would be positive 324. When you look at it in general form here, ax squared plus bx plus c would be 0. So then the axis of symmetry, be x equals the opposite of b, negative 324, divided by 2a, so divided by negative 3, and that's positive 108. Right? So that, like I said, the axis of symmetry is going to be at 108. And then what is the area at 108? Well, again, I'm going to go back to factored form here. That'd be 108, right, for x. Again, you can put 108 here, 108 there in the non-factored form. I'll do it up here. Now, half of 108 is 54 times 3 would be 162. And then 324 minus 162 would be 162 again. Right? So, and there's your length and width. Those are the dimensions that they want. Right? But if you were to multiply these, 108 times 162, let's see, 108 times 162, it's 17,496 square feet. Right? That would be the largest area this farmer could achieve. like that, and then you have a parabola, right, like this. But the highest area possible is this, right? And then the picture that I'd be drawing is the following picture. Right, we said x is 108, so and remember I call these three vertical segments x, so 108 feet there, 108 feet there, 108 feet there, and then based on this would be 162, and this would be 162 as well, and if you add all those up, that's 648 feet. All right. But the dimensions of the rectangle are 108 by 162. And that's what they want. They want the dimensions that give me that largest area, that maximal area. So 108 feet by 162 feet. Great. And again, please, read through the answer explanations. Alright, so now we're back to defining the domain and range. Remember, the domain's all real numbers for these. You can plug in whatever you want for x. It's the range that we need to worry about. So again, I just need to know the vertex and whether or not the parabola is opening up or down. Right. So I'll write this one out again. So here we have f of x equals, and they gave it to us in general form, 1 times x squared plus 6 times x plus 14. A is 1, so the parabola is opening up. Right, that's a positive number. It's going to look like this. So the range will be whatever the y value is for the vertex to infinity, right, going up. And the value of b is positive 6. And then we can say the axis of symmetry would be at x equals, negative 6 divided by 2. So x equals negative 3, right, negative b over 2a. And plug that in, right, f of negative 3 would be 5. That would be a 9 minus 18 is negative 9 plus 14 is 5. So negative 3, 5. But this time, it's opening up. So I know it does this. Right. Something like that. So again, the domain's all real numbers, no problem. Right, that's always the case for these quadratic functions. The range, however, is just the values 5 and up, right, from 5 to infinity. Including 5 though, or the way they're writing it, you say f of x, say the outputs are always greater than or equal to 5. Right. And that's this first option here. Okay. Alright. We're back to projectile motion. Again, they're just giving us our equation, our quadratic function. So here a ball is launched directly into the air at a speed of 40 feet per second from a platform located 10 feet in the air. The motion of the ball can be modeled using this function, where again f of t is the height of the ball off the ground in feet this time, and t is time in seconds. So when in seconds will the ball hit the ground? Right, and write your answer to the nearest hundredth of a second. Do not include units, right? So don't write seconds. Just write the number. Round it to the nearest hundredth. That's 2 decimal places. Right. All right, so this is very similar to the problem we had earlier. Right, it's f of t equals negative 16 t squared plus 40t plus 10. So again, if I were graphing this, showing you the motion of this ball, right, you got time in seconds here, and then the height in feet. And when time is 0, clearly you're at 0, 10. And then the ball, they said the ball was being launched from a platform located 10 feet in the air, and it's launched up, it comes down, and it's got to be a parabola opening down, right? The lead coefficient is negative. And the question is, again, where does this happen? where does the ball hit the ground? So basically, when is f of t equal to 0? When is the output 0? Now there are going to be two answers, right? But one of them will be negative, right? If you were to continue the parabola over here, it would hit, it would hit the horizontal axis over here, but that's at a negative time, so we're not going to consider that one, right? We're only looking for the one with the positive time. So I have 0 equals negative 16t squared plus 40t plus 10, and we can use the quadratic formula. So t equals, now if you want, you can shrink the numbers by dividing everything by 2. They're all multiples of 2, but I'm just going to punch in the quadratic formula. So the opposite of b, right, negative 40 plus or minus square root of 40 squared minus 4 times a is negative 16 times c is 10. And all this divided by 2 times a, which is negative 32 in the denominator. And once again, I'll go back to the Desmos calculator. We'll punch this in. So the numerator, parentheses, we have a negative 40, then with the plus, and then the square root of 40 squared minus 4 times negative 16 times 10. And then all of this divided by negative 32. Right, so that's a negative answer. Negative 0.23 if I was rounding to 2 decimal places. So that would be this value over here, right? Approximately negative 0.23 seconds. But again, it's negative. That doesn't mean anything. That doesn't make any sense with the launching of a ball. So it's the other one, right? So I'm just going to, instead of copying here, I'm just going to change this plus to a minus, and there we go. 2.729, so this would round to 2.73, right, if I'm going to the nearest hundredth. 2.73. This is approximately 2.73 seconds over here, and that's what they want, right? How long would it take to hit the ground? And all they want's the number, right? Don't put seconds. 2.73, right? Rounded to the nearest hundredth. Great. All right, next. And find the x and y intercepts. All right, so again, the y-intercept, no problem. Plug in 0 for x, you get 20 for y. So 0, 20. All right, I just have to fill in the spaces, the coordinates. They have the parentheses for me already. That's no problem. All right, it's the x-intercept that I'm going to have to do something else, right? All right, so here they give us options. Now it says select all that apply, right? There might be more than one. All right, so again, I'll write this out. We'll set the output equal to 0 and find the x-intercepts, if it has any. Remember, if it has imaginary solutions, then there aren't any x-intercepts. But I don't think that's happening here. Right? So we have f of x equals 6x squared minus 23x plus 20, and then find the x-intercepts. Right? So just set f of x, the output, to be 0. So we have 6x squared minus 23x plus 20. When is this equal to 0? Okay. So we can use the quadratic formula, right? It's already set up in that way. Ax squared plus bx plus c equals 0. You can try factoring. I mean, 6 times 20 is 120. I'm trying to think of factors of 120 that would add up to negative 23. We got 12 and 10. That makes 22. 20 and 6. Yeah, so if you want to play around with that, fine. But I'm just going to jump to the quadratic formula. So the opposite of b, right, positive 23, plus or minus square root of b squared. Now negative 23 or 23 squared, be 529. That's 23 squared. 2 times 26, 52, 529. And then minus 4 times a times c. Well, that'd be 480, right? It's 24. 4 times a is 24. 4 times 6 times c. Right, 24 times 20 would be 480. And then all this divided by 12, right? 2 times a. All right, so this is 7, right? Because 529 minus 480 would be 49. So this is just 7 square root of 49. So we have two solutions here. X equals 23 plus 7, which is 30. 30 divided by 12, which would be, let's see, 30 divided by 12. That's 6 times 5, that's 6 times 2. So 5 halves. All right, 5 halves. And the other one be 23 minus 7, be 16 divided by 12. And that's 4 times 3, 4 times 4, 4 times 3, so it's 4/3. And there you go. Those are the two solutions. So the two x-intercepts would be 5 halves 0 and then 4/3 0. And since these ended up being fractions, right, since this square root was a perfect square, the square root of 49 a perfect square, that means this could have been factorable. This actually factors the 2x minus 5 times 3x minus 4. And you can check that out. Right, so yeah, so there's negative 8x and negative 15x to make 8 and 15 would have been those factors. Right, just didn't see that earlier. Okay, so 5 halves and 4/3. Right, so back here, 5 halves comma 0, 4/3 comma 0. There's your x-intercepts. Alright, so that objective's done. I'm thinking we're reasonably close to the other ones. Now domain and range, again, just needed, this one's even easier. It's a quadratic that's written in that standard form. I'm assuming you remember what the standard form or vertex form is from sections 5.1 part 1 and 5.1 part 2. So the domain, I'm going to, they're saying put in interval notation. So that's, negative infinity to infinity. It's all real numbers with the parentheses on the ends, right? Now the range, lead coefficient's negative, -2, so this is opening down. So this is going to be, the range will be from negative infinity up to some value, right? Up to the value of the y value of the vertex. And remember what the vertex would be here. This is, x minus h squared plus k. The vertex is hk. K is the y value of the vertex, -6. So it's from negative infinity up to the y value of the vertex, -6. And don't forget to put a bracket on -6, right? -6 is actually used. And again, if you want to look at the graph of that and see that the range is, from negative infinity up to -6, go ahead. But if you know the vertex and you know how it's opening, should be no problem. And again, they talk about the standard form again here, right? The vertex form. All right, so same objective, and then once again, vertex form. So this should be easy. Domain, all real numbers, right? Negative infinity to infinity. Not a problem for that. I'm not seeing infinity here, but if I change this to basic, there's infinity. So negative infinity to comma infinity, and the parentheses are closed. Now this is opening up. See the positive 2, the lead coefficient will be positive. So it's opening up. So the range is from whatever the y value of the vertex is to infinity. So I'm going to put a left bracket. The y value of the vertex would be this plus 5 here. Right? The x value would be -6, but the y value of the vertex would be 5. So we're going from 5 to infinity. And just close it with parentheses. Always parentheses on the infinities. There you go. And again, if you want to look at a graph of this on Desmos or draw a graph yourself, go ahead and see the domain and range that way. That should have been simple though, especially if it's in vertex form like that. Alright, so back to another projectile. So here, the path of a baseball hit 3 feet above the ground is modeled by this function, where f of x represents the vertical height of the ball, like the height off the ground. X is the horizontal distance. Okay, so x is not time. X is not time this time. X is how far horizontally from the batter the ball is, and f of x is how far vertically off the ground the ball is. So how far across the field in feet will the ball travel before hitting the ground? Right, so again, I'll draw this. All right, so here f of x is negative 0.01 times x squared plus x plus 3. So again here, x, this is the number of feet that the ball has traveled horizontally. And then f is also in feet, right? The output's in feet as well, but this is the amount of feet it's off the ground. And we have 0.3, right? The ball was hit 3 feet off the ground and goes and then comes down at some point, right? And we just want to know where that is. Where is that? Where does it hit the ground? How far has it traveled horizontally across the field before it hits the ground? So again, it's just finding the x-intercepts here. All right, let f of x be 0. Right, where is the output? 0. Now once again, there will be two answers, one negative, one positive. We only care about the positive one. So where is negative 0.01x squared plus x plus 3? Where is this equal to 0? And again, I'll just use the quadratic formula here. So x equals negative 1 plus or minus the square root of 1 squared is 1. Now 4 times a times c, 4 times c is 12, 4 times 3, then times negative 1/100th, that'd be negative 12/100ths, but you're subtracting that, so it'd be plus 0.12, right, like that. There's 4ac minus 4ac, and then but it'd be plus because there's negative, and then divided by, and then negative 0.02, right, 2a. 2 times a, 2 times the coefficient of x squared. Alright. So again, I'm going to go to a calculator here. This is going to give me two different answers. Actually, the one with the minus is going to work out to be positive, because if I take a negative number and subtract something more, it'll be more negative. Subtract a positive, it'll be more negative, and a negative divided by negative is positive. So I'm just going to plug in the negative one back on the calculator here. So in the numerator we have negative 1, then the one with the minus the square root of 1.12, and then all that divided by negative 0.02. So 102.92, if they say round to the nearest hundredth, I believe. Rounded 2 decimal places, yeah. So 102.915, so 0.92 feet across the field. So this is about 102.92 feet across the field. That's how far it would have traveled before it hits the ground. And again, there is a negative answer, but I don't care about that one. Wouldn't make any sense. All right, and all they want is the number. Don't enter, they already have the word feet there for you. So 102.92. Great. All right, so one more like this. It's the same kind of question. Here's a thing talking about how an object is launched in the air and how it's going to travel through the air. T is time in seconds. F of t is height in feet off the ground. How long in seconds will the object be in the air before hitting the ground? All right. Yeah, so again, I'll write this out. set the output to be 0, and basically like finding the x-intercepts, finding the t-intercepts. So we have f of t equals negative 16t squared plus 32t plus 8. Set this equal to 0. I'm just going to replace it with 0 here. Seriously though, if you just, I notice that all these are nice multiples of 4. I'm going to divide everything by negative 4. We get 4t squared minus 8t, and then minus 2. And if I just divide everything by negative 4, that's all I did. Divide both sides by negative 4. Alright, and now we have some smaller numbers to work with. And I'm actually gonna solve this one by completing the square. So we have 4t squared minus 8t equals 2. Adding 2, then dividing by 4 again, we have t squared minus 2t equals 1/2 right after dividing by 4. Then complete the square, add 1 to both sides. So this is 3/2. This is t minus 1 squared equals 3/2. So t minus 1 equals positive or negative, square root of 1.5. I'll just put, so then when I go to the calculator, because they asked us to round it nearest hundredth again, 2 decimal places, and then I add 1. T equals 1 plus or minus the square root of 1.5 seconds. Obviously I'm going to use the plus 1 this time because that'll give me the positive answer. So t is approximately whatever 1 plus the square root of 1.5 is. So 1 plus the square root of 1.5, about 2.22. If I round to the nearest hundredth, 2.22 seconds. And that's all they want. Right? Again, there is a negative answer, but it doesn't make any sense with the problem. Or if you were drawing it, if you were graphing it, drawing the path of the ball or the object. And they don't want any units, right? They just want the number 2.22. Great. All right, so that objective's done. It's got one more objective left. That was the maximum, these word problems. All right, so once again, similar to the second example we saw in this objective, got all this fencing here, and it's another rectangle. So the area is length times width. This time there's 162 feet of fencing. And again, what are the dimensions? What are the length and width of this rectangle that will enclose the maximal area, right, the largest area? All right, so once again we draw. So here's this picture they gave us. Nice rectangle with a little, again, I'll call these x feet, and x feet. And there's 162 total feet of fencing. So that means, take 162 minus the 3x, and then each of these sides will be half of that. All right, so 81 minus 3/2 x. So that's 81 minus 3/2 x feet, 81 minus 3/2 x feet. And then the area, right, which again I'm calling a of x, as I call my variable x, is just the length times width, x times 81 minus 3/2 x. And if you distribute the x, that'd be negative 3/2 times x squared plus 81x. If you were making a graph, right, obviously if x were 0, the area would be 0. And also if x were 54, right, 1.5 times 54 is 81. That would make that 0. You'd have a 0 area as well. So what's halfway between those? It's 27. So when x equals 27, there's your axis of symmetry. Again, if you do the negative b over 2a, negative 81 over negative 3 would be positive 27. Negative b over 2a. And if I plug this in, right, the area at 27, I'll plug it in the factored form, is 27 times, and then 81 minus, now 3 halves times 27 would be 81 halves. So that's 162 halves minus 81 halves is another 81 halves, right? So I don't know if they want decimals or fractions, but there's your length, there's your width, right? 27 times 40.5, right? 81 divided by 2. There's your length and width. So if these were all 27, and this side here was 40.5 or 81 halves, same thing with this side, the area would be the largest possible, and it's whatever 27 times 40.5 is. But they're not asking us for the area. They're just asking us for the dimensions that would give us that largest area. So 27 feet by, you can put 81 halves, but I think 40.5 will also work. Great. Yeah, it's pretty much the same setup as earlier, just with some different numbers. And the last question should be from this same, it's the same exact thing. Same exact kind of problem. Alright, well, let me just do that again. And again, what are the dimensions of the region that will enclose the maximal area? So pretty much the same picture. Call these x, and x feet. They said that this time there are 234 total feet of fencing. So if these are 3x, that means there's 234 minus 3x left, and then these two sides, must be half of that. The half of 234, 117. So 117 minus 3 halves x, and same thing up here, 117 minus 3 halves x. All right, then the area of this whole rectangle, this whole region has an area of x times 117 minus 3 halves x, or negative 3 halves x squared plus 117x. If you were graphing, right, 0, 0, if x were 0, again, if x were 0, the whole thing would be 0, the output would be 0, the area. And so that's 3 times 39. 3 times 39 is 117. 1 times 2 would be 78. And you got 39 in the middle. The axis of symmetry would be at x equals 39. Right? And you can do the negative b over 2a, right? Negative 117 divided by 2a would be negative 3. 117 divided by 3 would be 39. And then what's the area at 39? Well, back in the factored form here, that'd be 39. That's your length. Right? If these are 39, 39, and 39 feet times, and then where are these other two lengths? Well, 3 times 39 is 117 halves, so this would be another 117 halves. Right? 117 minus half of 117 would be another half of 117. So you have 39 by, now you can probably write 117 divided by 2. But let's do, 117 divided by 2 would be 58.5, right, 58.5 feet. So if this is 58.5 feet and 58.5 feet over here, there's your rectangle with the largest area possible using up 234 feet of fencing. But this is what they want, right? They just want the dimensions. They don't want the actual area. Now, if they wanted the actual area, you would multiply these. Right? But I'm not doing that. So the dimensions of the rectangle that would give you the largest possible area would be 39 feet by 58.5 feet, 58.5. Great. All right, and that should be it for this preview version of this assignment. As I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, so I'm hoping that the questions are similar enough so that watching me do them here help you out in some way, when you work on the assignment yourself. And thank you very much for watching.